I just was chilling. Okay. Um, okay, so let's talk about 4.6. So we are talking about, so the first one is talking about standard linear regression. So I'm going to go over this, even though it's a little bit easier. So this is pretty classic where we have basically we're saying yi is distributed as normally xi transpose beta sigma squared. Okay, and this is actually standard linear regression and based off our normal assumption, because usually we're saying that yi is equal to, like for example, beta naught plus beta 1 x1i plus beta p x1p, or sorry, x pi plus epsilon I. And then we assume, right, epsilon I is distributed normal 0 sigma squared. And so if you actually just make this assumption that this is directly the same as this, like these are the same assumptions. So this is another way of saying like under the Gaussian assumption, this is another way of stating standard linear regression. Okay. So then the first one asks you to find the likelihood. So let's talk about that. So let's find the likelihood, right? You always just want to find, so we need to find the likelihood of this. So you always just want to find it for one I and then just do the product over all the I's, right? If they're independent, and these are clearly independent. He didn't write this, but he's saying that this is IID basically. Well, they're not IID, they're independent because actually they're each different because they each have a different mean. But if we remember basically what the normal distribution is, then for yi, you can just write it as 1 over sigma root 2 pi, and then x of negative 1 over 2 sigma squared, yi minus the mean, which is just xi transpose beta squared. Okay. And so then the likelihood is just literally just doing the product over I equals 1 to n. It's really easy. So this is the likelihood. For standard linear regression, okay? And you can simplify this to put further. So I would recommend simplify this a little bit. Simplify. I'm not going to do that, but and if you'll notice, this term up here ends up being what you minimize, which actually ends up being the same as what you would do for least squares regression. So that's why the estimates are actually the same. Okay, so now let's talk about logistic regression. Okay, so logistic regression is a little more tricky, but let's talk about it. So what is logistic regression? So I don't think maybe you've heard of it, maybe you haven't. Deanna, have you ever heard of it?
I've heard of
Oh,
it,
you've
but I
heard of
don't know
it?
how
Have
to
you ever
like
like
do it.
done it? Okay, so logistic
Not
regression,
really.
the basic idea is that you have a setup in which yi, so the response variable, is a binary variable. Okay. So what that means is that it's yi is either 0 or 1. Okay. And then basically the idea is we now want to estimate, we want to basically regress onto that. But the problem is that y can only be 0 or 1. So we want to create a situation where the response variable, so basically we want to create a situation where xi transpose beta, or our form of that, is between 0 and 1. So we never want a value, a prediction, to be greater than 1 or less than 0. We want them to be between, and then we do a cutoff. Typically it's 0.5, and we assign everything above to 1 and assign everything to 0. This regression is really important for machine learning if you've never done it yet. And so the setup now, instead of having what we had before, where basically it's like yi is equal to, I'll just say x beta plus epsilon, now we have instead basically that log of the probability that yi equals 1 over the probability of yi equaling to 0, okay, is equal to xi transpose beta. So now instead of, or I could also write this as better probably, xi equals xi transpose beta. Instead of this simple relationship, we have this much more complicated relationship, okay? And they want you to find its likelihood, okay? So B, they say find likelihood for yi. Okay, and you're like, what the heck? Well, what you need to remember is that a binary random variable is going to have a Bernoulli distribution always. So yi is distributed as Bernoulli with some value pi, right? That's with some, what's the word? What's the word? parameter pi, right? Where this is going to be equal to basically pi yi distributed as pi yi times 1 minus pi 1 minus yi. And remember, pi is actually just this thing up here. So it's going to be the probability that yi equals to 1. Okay. So really the challenge here is we need to find pi. Okay. So again, I know it's a little confusing, so let me know if you want me to stop. But then once we find pi, we then have the likelihood. So then we have pi, we can plug it in for what it actually is in terms of xi transpose, in terms of beta, basically. We need to make it a function of beta. And then we can just take the product, and it's very quick, right? And that gives us the likelihood. So we need to isolate what probability of yi equals to 1, and we have it up here. So let's just kind of look at this. So we don't care.
You make
What's
both
up?
sides, or so you just add both sides to the e, right? To get rid of the natural log.
Yes. I'm going to make a first step though. Is we want to get rid of this. So how can I rewrite this in terms of this top part? I mean, I can write this right. Yeah. What's up?
Oh wait. I don't know if this is right, but is it 1 minus the probability of yi?
Exactly. Yeah. Because remember, yi is a binary variable. It's either 1 or 0. So probability equals to 0 is exactly equal to 1 minus probability equals 1. So let's replace that first. And then exactly what you said. The next step is to exponentiate. So let's do that. So x. So that gives basically probability of yi equals to 1 over 1 minus probability of yi equals to 1. Oh, sorry, this should be 1. Apologize. Is equal to x of xi transpose beta. Okay. And then from here, we can just simplify. So let me just do some math for it. So it's this, and then equals to basically xi transpose beta minus xi transpose beta times probability yi equals to 1. So I just multiplied this denominator and multiplied it by this. And then just simplifying, you end up getting that. So if I add this over, I get probability of yi equals to 1 times 1 plus x of xi transpose beta is equal to xi transpose beta. And then you get probability that yi equaling to 1 is equal to xi transpose beta over 1 plus xi transpose beta. And notice that this value here will always be between 0 and 1, right? There's nothing else. So if I do 3 over 4, that's between 0 and 1, 100 over, and this is always positive as well. So it's, or 0.1 over 1.1, that's between 0 and 1, right? They're never not going to be between 0 and 1. So that's how you kind of know you've done it correctly. And then, so then we have this, okay? Does that make sense? I just literally from this step, yeah, what's up?
I think it makes sense.
Okay, cool. So yeah, really the step, everything I did from here basically to the end was just algebra. I just said, okay, let's just, the only quirky thing was replacing it with 1 minus pi. So now remember, we said yi is Bernoulli for some pi, and the pi is equal to this. So now we found the pi, so we can replace now, we can find the likelihood now. So for the individual one, I'll write it for individually. It's going to look like this, which means it's going to be xi transpose beta over 1 plus xi transpose beta to the yi times, and people sometimes rewrite this in different terms, just FYI. So if you look up this regression or you see this regression, it might be written in a different way, but I'm just not going to bother. 1 minus xi transpose beta over 1 plus xi transpose beta. And so I don't want to give the full answer, but what you end up having to do now is now take the product, okay, from I equals 1 to n and simplify it a little bit, and you'll kind of see what ends up happening. It doesn't simplify like extensively really, but you know, um, so that's pretty much, and then yeah, so simplify, and then you need to take the derivative with respect to beta, which again is a little bit tricky, but it's really just a calculus problem. So if you can think about it, you know, it's like a product rule and it's a little bit annoying, but, and you're gonna get something that's not, I believe, if I remember correctly, I'm like 90% sure of this. You'll get something that isn't really easily solvable. So don't actually try to solve it because you can't, I don't think really well. Like it's a non-solvable expression from what I remember. So typically when people do it, you end up having to do optimization methods instead. So again, simplify this.
Sorry.
Yeah, what's up?
Sorry. Could you explain like how you got to the last step?
Which step? Writing it like this?
Yeah.
So what I kind of said before was basically, and this is in the hint in the problem, he says that any binary variable, right? Any binary variable is going to be a Bernoulli random variable. Okay, so we know yi is distributed as a Bernoulli with some parameter pi, and pi is equal to the probability that the Bernoulli random variable is equal to 1. And so with that, I can write it as the distribution as basically pi to the yi times 1 minus pi to the 1 minus yi. And that's just if you look up the Bernoulli distribution, that's what it is. So then the question becomes, okay, what's pi? Because that's the parameter we defined, and that's equal to the probability that yi is equal to 1. So then I went back to what we were given, which was this expression here, right? We were given this expression right here. And I said, okay, well, we need to solve for probability that yi equals to 1. And so we can do that by replacing the probability that y equals 0 with this, and then basically just going through this whole process, which again was just a bunch of algebra. And then we got that the probability that yi is equal to 1 is equal to this value right here. Then from here, all I did was plugged in this term, so xi transpose beta over 1 plus xi transpose beta, the pi from the Bernoulli expression above. So that was replaced with just pi. And then the likelihood, right, you just multiply them all together because they're all independent. But I didn't simplify that.
Thank you.
Does that make sense? Okay, cool.
Yeah.
And then it says take the derivative with respect to beta. Again, that's just like annoying to do, but or it actually has the gradient. Oh no, that's okay. Yeah, it's a gradient. Okay. So that part's just calculus. The next thing is ask you to find basically ask you to find the expected value of y.
I'm sorry, but
Yeah,
can you remind me of the gradient? Because I have learned that in a math class, but I kind of forget that.
Yeah, I forgot how to do that too.
Yeah.
Wait, hold on. Let me check
that.
what gradient means.
I've never seen that after that class. Yeah.
Is gradient just the... Hold on. Oh, okay. So sorry, the gradient. So sorry, I should be more specific. Okay, I forgot. I'm also very bad at calculus sometimes. What the gradient would basically be, it's going to be the vector of wait, hold on. Gradient with respect to beta. Would it just be the partial derivative? Would it even be a vector? Or does he want you to do it for each beta one? Okay. So I know what he's saying. So really you just need to take the derivative with respect to beta. Okay, and so you can just consider it like that. What a gradient is, it would actually be, this is actually going to be a vector when you do this. So this is actually a vector. It's going to be the partial derivative with respect to beta 1 through the partial derivative with respect to beta p. But I don't think it matters when you do this. Like, I don't think you have to find these all individually. I think you can just write it as, unless maybe it's easier, but this is the gradient, would be the derivative with respect to each of the beta values, beta 1 through beta p. But if you just take it with respect to the full vector, it should also work the same. Although there's a potential that maybe taking the gradient is what you're supposed to do, because you usually, when you do this, you do gradient descent. So maybe that's why. So if you can take the derivative with respect to just beta, you can just say that, and then say, oh, this will be of this vector.
Well,
and
do
maybe
you
you can,
need to
yeah.
take derivative to the likelihood function, or
Yes, yeah, the likelihood function. So this thing, the product of all of these together, which when you simplify it will look different a little bit, not much, but a little.
I don't think I can solve that. Really.
Okay, let's think about this then. Okay. He also didn't give me the answer for this one, so I'm not exactly okay. So let's think about this. So the product is going to be okay. So you have, I'm just trying to think about this. So you have x1 transpose beta over 1 plus x1 transpose beta, the y1 times 1 minus that. I'll just call this ci. I'm just going to call this c1. I'm just going to replace this with c1 to be quicker. 1 minus y1 times c2 y2, 1 minus c2, 1 minus y2.
Does it just end up being like, oh wait, never mind. Sorry, ignore me.
No, you're good. Huh. I'm not simplifying this. Okay, so this is what I have. It says gradient of log. Okay. Okay. So yeah, there's actually not a very good way to simplify it. You pretty much leave it as this. What you can do, I will say, is you can, okay. My recommendation would be find the log likelihood. Okay. So there's actually really no way to simplify this, like when you derive this. So find the log likelihood, which is going to be the sum, because this will be a lot easier when you take the derivative, right? So that would be the sum from I equals 1 to n of yi, and then the log of this should simplify this a little bit. Log of xi transpose beta over 1 plus xi transpose beta plus 1 minus yi log, I'm just going to call this again ci, just to be slightly quicker. And then what you would then actually do is take the derivative with respect to each beta I. So derivative with respect to beta I is going to be basically, let's simplify this. This will be log. So this expression is going to be log of xi transpose beta minus log of 1 plus xi transpose beta, which is going to equal xi transpose beta minus This can be simplified. How can this be simplified? It's such a vague memory. Can this be simplified?
Is that multiplier? Like inside log? I can't really recall, but is that just log 1 times log?
No, because it's only when it's so it's log additions of logs turns into multiplication. There's a way to do this. Simplify this. That I will. So this is 1 minus c. And you also could just not. You also could say this is yi times this minus log and just see what happens. Plus 1 minus yi log of 1 minus what I had before. Sorry, I'm just trying to think. And it's still, you have to sum. And then, yeah, so you just take the partial with respect to beta 1, beta, or I'll call it beta j. And so you just kind of go through each of these and like only care about beta j, basically. So, right, xi transpose beta is really just xi1, so beta naught times 1 plus beta 2 times beta 1 times xi1 plus beta 2 times xi2, so on. And so you just take this derivative. Sorry if I'm not explaining that great. But basically, you need to take the derivative with respect to one of the beta values. This is probably the trickiest part, I think. So I wouldn't worry too much. Can't get it. Well, you know what I mean. Try to work through that a little bit. I'm like close. I think if you just simplify things a little better, it'll be pretty obvious. But what's really important is basically you have take the log, I think is really the key part. And then it turns into a sum. And then you can take the partial derivative. It just becomes a calculus problem, really. Taking the partial derivative with respect to the beta I. And so if you need to write everything as sums, I'd recommend doing that. So all these like, can be written as like a sum, really. Like even this can be written as a sum. And then you can, like this thing in the denominator can be written as a sum. So if you need to do that, that's that one. The other two ones in this problem are not as difficult. So then it's asking about basically the expected value of y and the covariance of y. And my recommendations for both of these is that just look at, so this will like look at like a Bernoulli, because this is really just the joint of a bunch of independent Bernoullis. And so the expected value is going to be the expected value for each independent Bernoulli. Same with this one. You should notice that the yi values are independent. So that should say what the off diagonal should be. That means that yi is independent of yj, right? So obviously the covariance of yi, if I is not equal to j, covariance of yi and yj is going to be equal to 0 if I is not equal to j. And then for the variance of yi, which is going to be the diagonal values, notice that you can use the variance properties of a Bernoulli. Okay. Basically, each yi is a Bernoulli. And you know what the expected value of Bernoulli random variable is. Same with the covariance of y. What I'm saying is basically the diagonal is going to be just the variance of a Bernoulli thing, a Bernoulli random variable with this given pi. And then the off diagonal, we already know they're independent. So we know they're going to be zeros. Okay. Hopefully that helps a little bit. I know I couldn't solve all of it. But I think there's a little bit of like calculus. Hopefully it's just like calculus left you have to do instead of like, more of the statsy stuff, which I think is a little, if you don't know where to start, you don't know where you're going. Any other things about that one? As I was saying, this is definitely the most difficult one, like by far. Okay. Well, I have 10 minutes, so I'll try to talk about the earlier ones as much as I can, unless you have any questions about this one. Okay, so for problem 4.1, which is also confusingly 4.2, I came up with a problem that's really similar to it. So basically, let's say you have, we know that basically y of t is equal to beta naught plus epsilon t. And we have n is equal to 2. And we have a data vector, which is just y is equal to 5, 6. And they say, basically, draw the data in two-dimensional space. And then also identify orthogonal projection of y onto basically the image of x. He says, they say lx, which is equal to the image of x. So when I did this problem last year, I remember a lot of people were confused as to what x was. He actually says in the problem that this is equal to the image of 1. And so the reason is that you only have this beta naught variable. Okay, so when you only have a beta naught variable, your data typically, right, is equal to like x. Your data matrix is usually like 1s, and then the rest of your vectors. So then it's like, okay, x1, 1 through x1, n, and so on and so on. So when you don't have any data, your whole data matrix is just going to be x. It's just going to be the 1 vector. So to draw this in two-dimensional space, what that means is this is going to be the L of x, or the image of x. I don't know where the L comes from, but so this is L of x, aka image of x, which is just the image of the 1 vector. So this is just like 1, 1. So this is like x. This is like really line x equals y. You also can think of it as like 1, 1. And then we have y, which I'll draw in blue, which is going to be 5, 6. And I won't really draw it specifically, but
Wait,
five,
sorry,
6.
could you repeat why the image of x is equal to the image of 1?
Yeah. So in our data model, we have basically that yi is equal to just beta naught plus epsilon I. And so when we only have the beta naught vector, right, it means that the only data we have is the row of 1s that we typically associate with the beta naught vector.
Oh, okay, that
So
makes sense.
Yeah. So when you have like, remember, I don't know if you've done this or how much you've seen this, but like when you usually do a data matrix X, you always have to augment it with a column of 1s that correspond to the beta naught value. So in this case, we only have those 1s, right? So then 5, 6, I'm sorry if this is above or below incorrectly, but I'm just too tired to think. So this would be our y vector, which would be 5, 6. Okay. And so to draw out what's happening, okay, they ask you to draw beta naught. So they want you to find, to identify beta naught hat, mu hat, and E. So when you have a data vector, what you're doing when you project, to find the orthogonal projection of y onto this, you just take this value and then you drop it down. And then this here, this is the projection of 5, 6 onto 1, 1, or onto x, I should say. And so to identify everything sort of geometrically, right? This is also known as, this is basically mu hat. This is mu hat, okay? This is our estimated value because this is what, when we project our data vector, okay, onto the subspace of our, we project our y vector onto the subspace of our data vectors, right? That orthogonal projection, that's our estimate. So we're saying, okay, we have this data vector. What's the closest we can get in our data subspace? This is our y vector. Where can we get? So we take the orthogonal projection. So this is mu hat. E is going to be this error vector here. So basically E is saying, okay, how much do we mess up? So it's really like y minus mu hat, right? If you notice, this is y, this is mu hat, then E is going to be y minus mu hat, which is exactly what we want, right? Now, to actually find this vector, you'd actually have to do the math of finding the projections. Just really quickly, if you don't remember, the projection of 5, 6, for example, onto just a vector, which is 1, 1, would be given by 5, 6 dotted with 1, 1 over 1, 1 dotted with 1, 1 times 1, 1. And I'm not going to do the math, but it ends up being 11 over 2 times 11 over 2. So that's what mu hat is. 11 over 2 over 11 over 2. And in regards to beta naught, so beta naught would be what you're multiplying this 1, 1 vector by. So then I'll do it in rainbow. So then beta naught hat would be, since we have this is basically 11 over 2 times 1, 1. Or sorry, this is mu hat. So then beta naught hat would just be 11 over 2. So it doesn't really have like this would be 11 over 2. Or like this would be 11 over 2, which is beta naught hat. It's like how far you would go up. So hopefully you can do that. Obviously the one in the homework is different. It's not the exact same numbers, but hopefully you can kind of figure out how to do that. So that's the first one. The next one, basically all you need to know. So again, I know I'm running really short on time, but the next one, they give you, so 4 point, I guess I'll say 2, they give you the X transpose X inverse matrix. And all you need to know is the variance of beta hat is going to equal to S squared times X transpose X inverse. And so, well, sorry, this is variance hat of beta hat. So the estimate of variance beta hat is going to be that. And so from here, you can find all the variances. So basically what ends up happening is if you take this matrix, and let's say it's like a 3 by 3, then this would really be like a variance of beta hat, variance of beta 1 hat, variance of beta 2 hat. And then all these are just like, it's pretty obvious. Like this is the covariance of beta naught hat with beta 1 hat, and so on and so forth. So then you just grab all these. And then for hypothesis testing, I know I'm almost out of time, the standard error of, for example, beta 1 hat is just going to be the square root of the variance hat of beta 1 hat, which you can also get from the matrix very quickly. So to do hypothesis testing, all you need to do is take the standard error, and then to get the t value for that, to get the t distribution, it's just going to be, to do hypothesis testing, we have the standard error. The only thing you need to do is the t distribution, which is just going to be, remember, it's going to be t of n minus p minus 1, where p is equal to the number of parameters. Or sorry, I should say number of variables. It's a little confusing. So in this case, it would actually be yeah. So in this case, it'd actually be 2. So you'd say t of n minus 2 minus 1, which equals t of n minus 3. It's not t minus 3 minus 1. It's a little confusing, but the 1 is added for actually beta naught.
Sorry,
So what's up?
but we cannot calculate the t-value right in this question because the confidence level is not given. Like for the
Oh,
I actually
you
I use the confidence interval to do the hypothesis test.
So you
So
can do hypothesis however you want. When they ask you to hypothesis test, you can just state which one it is. Typically 95% is what confidence test you want to do. But technically you could do 99% if you just state that you did 99%. Do you know what I mean? Like just you have to clearly state which one you're doing.
okay.
I know it's weird they don't give you a level, but if they don't give you a level, just state what level you're using. Typically I would say I always just would say 95%. So that's how you do that. I'm out of time.
What would be n? Sorry.
What's up? No, go.
What would
What's
be
your
n?
question? What would be what?
N?
N would be given to you. So they say in this problem, they say n is equal to 15.
Oh, okay, cool.
N is the number of cases, the number of like subjects or whatever, cases, whatever. Okay, I'm sadly out of time. Sorry, that last one took a lot more time than I thought it would.